Hello and welcome to our lecture on solids, the first phase of matter which we are going to be discussing. A phase of matter describes different properties of materials as they are scaled up to large scales and are placed under different temperatures and pressures which cause phase changes. Common phase changes include those between solids, liquids, and gases at different pressures and different temperatures. And each of these changes are going to have specific properties, whether it's a solid, a liquid, a gas, or a Bose-Einstein condensate, or plasma, or any of the other types of things which we call phase changes. The first phase of matter that we're going to look at are going to be solids, which are materials which are relatively hardy and don't change volume or their shape depending on the container that you place them in. A type of solid is a crystal, where a crystal is made up of atoms or molecules arranged in rigid and ordered crystal structure or crystal lattice. These crystal or lattice structures are defined by a repeating pattern, such as the honeycomb pattern shown on this slide, which is actually the reason that I chose the honeycomb pattern in the first place, because it describes the crystal structure of graphene, which is two-dimensional carbon and is very useful for the cutting edge of material science today. On the right, we see a reciprocal lattice, which is a lattice caused by the reflection of beams of light or particles, which give rise to a ordered structure, which is called the reciprocal lattice, while the real lattice is the initial structure that the atoms in the crystal align themselves to. As you can see, these are two different lattices, but they are mathematically related by something called a Fourier transform. Non-crystalline solids are said to be amorphous. In the amorphous state, atoms and molecules in a solid are distributed randomly. Rubber, glass, and plastic are among the materials that lack an orderly, repetitive arrangement for their basic particles. In many amorphous solids, the particles have some freedom to wander. This is evidenced in the elasticity of rubber and the tendency of glass to flow when subjected to stress over long periods of time. Elasticity is the capability of a solid to change its shape and bounce back to its initial state. Steel is an excellent elastic material because it can withstand large forces and then return to its original size and shape. Because of its strength and elastic properties, it is used to make not only springs but construction girders as well. Elasticity is also defined by Hooke's law, which is described by the relationship that force is proportional to the change in x, the change in displacement of an object from its initial state. It is also a restorative force, which means that if you press out with a delta x and change the position of a molecule or an object which obeys Hooke's law, then it will press back inwards and try to restore itself to its original space. So this is seen in all sorts of materials, but the quintessential examples are a spring, where if you stretch a spring, it will pull back towards its resting place, or if you compress it, it will also push back towards its resting space, or a pendulum, such as the bob that you see in a grandfather clock, where when the bob is pulled to the side, the torque will pull back towards the center proportionally to the displacement from the center of the pendulum arc. There is a theory that I read in Charles C. Mann's 1491 where societies in the Americas made more use of tension than compression, while societies in the Old World made more use of compression than tension. The textbook brings up that stone breaks more easily under tension than compression, so a lot of Asian and African and European architecture made use of arches, where the stones are pushed together more firmly and held together by compressive forces if they are placed in an arch pattern. And this described a lot of European architecture. If you went to the Americas, instead of seeing arch bridges which were stone and held together by compression, You would see rope bridges which were held together by tension and were also very strong. It was still using science and an understanding of the world. It's just that this science looked different and was therefore dismissed by many European settlers who came after the fact. The density of an object is defined as the mass divided by the volume. The weight density is defined as the weight divided by the volume. It's a measurement of how much mass is in a given volume, kind of obviously and by definition. It depends on the material the object is made of and can be useful in finding the identity of a mystery material. Finally, we get to the square cube law and scaling. With the same density of materials, the strength of an object's legs slash trunks slash whatever goes according to the cross-sectional area of the material, while the mass goes according to the volume. So how strong your arms are related to how thick the tendons in them are, but how much mass those arms have to carry when you do a pull-up goes according to how much total matter you have in you, which goes up according to volume. An object which is twice as tall but maintains the same dimensions will be 2 squared equals 4 times as strong, but weigh 2 cubed equals 8 times as much. And this is why small animals are so proportionally strong and why elephants need thicker legs to support their weight than a mouse does.